find that. Not all braces are created equal. Okay, what's an event-to-event analysis?
You analyze where the plastic hinge forms and then reanalyze it to the next one.
Yep, it's this concept that we're going to take a structure, we're going to start loading it up, and that when the first plastic hinge forms, that doesn't necessarily mean that life is over. What's it mean? An event just occurred, right? An event just occurred. Much like humans have stressful events in their lives where they have to group together and keep moving, how resilient they are, right? This event-to-event analysis really runs through the gamut of structural resiliency, right? Pushes our system. So we get a first event to occur, we modify our structure, right? Keep on pushing, keep on going till the next event occurs, right? Modify the structure, keep on going. How long do we go? Till it fails. Well, some people might say that locally it's already failed. Some people might say a hinge is failure. What do you push towards? Till there's no more abilities for hinges to form, right? Till you form a mechanism, is actually the answer we're looking for. You keep going until you form a mechanism. And if you remember last time, we talked about it here. Okay, and this one was kind of a silly one to do, but it's good. It's illustrative. That we had a simply supported beam, and we kept loading, and our moment diagram looked like this, and we kept going until P over 4 was equal to our plastic moment. And once it did, our structure, we modified our structure, and we kept loading it. But it happened to be unstable, right? It happened to be unstable, and so it was over. Okay. Now this is Now we go to a more complicated structure, a fixed loaded with a load on it structure. And we start out and we get a certain moment diagram on our structure. And we keep increasing that load until what happens? Plastic hinge. Where's it going to form at? The highest moment, right? Plastic hinge is going to form wherever the moment's the highest. That happens to be on this problem on the right-hand side. Okay? So that's where the first hinge forms, and now we modify our structure, right? Then what do? Keep going, right? Okay, we keep loading our structure. Our structure now has a new moment diagram. And we keep going until what happens? This is really important. This is the point that you really need to wake up out of the rainy haze that is today and really pay attention, because this is what everyone screws up every year. What do you do? What's that? You add the first moments that were created from the first event-to-event analysis to the moments that are created from this additional load on our modified structure. That's exactly right, and that's the part that everyone forgets. But you add those sums together until what happens? Create another plastic hinge. Where's it going to be? Well, usually one of two places. Could be one of three places, depending on how complicated things are, right? Okay? And how do you decide where the second plastic hinge is going to form? How do you know? You do the math. And what are you looking for in the math? Yeah? No. No, it's wrong. The highest peak here means nothing. The highest M means nothing. It's where the highest combined moment is. It's where the highest moment from the first one plus the second one. The first one plus the second one. It's not about the peak here. It's about where the combination is the highest. Because if we think, this structure is still holding this moment. this moment still has to be in place. We don't get to wipe it off just because we formed a hinge. That moment is still locked into place. And that's why we change this to be P2. That's why we use a different P. And we load up P2 on our new structure until the moment from our first structure plus the moment from our second structure is equal to the plastic moment. Now, the way mathematically you do that is you set both of these equations up. You solve for both of these equations, and you look for the minimal P2, the lowest P2. That's the one that requires the lowest amount of load, additional load, to actually happen. Because if you solve this, and you don't worry, you'll do homework. You're welcome. And you'll solve this, and you'll find out what the P2 values are, and you can compare them to one another, and you're going to pick the lowest P2, because it's the one that would happen first. Does that make sense? Okay. So now we get another hinge to form. It happened to form over here. We do the same thing, right? We load the structure up. We get our new moment diagram. And when does the hinge form here? When the moment from the first plus the moment from the second plus the moment from the third is equal to what? M sub P. So at this point, we already know P1. We determined it in this step. We know P2. We determined it in this step. Now we're solving for what P3 we need. And that P3, P1 plus T, P2 plus P3 will be our failure mode. Oh, okay. What is the final moment diagram going to look like? Oh, I'm sorry. Before we go there, we should probably complete the story here by drawing our structure again. Hinge, hinge, hinge. I try to add P4. And can I add any P4 to that? No. It's a mechanism. It's a mechanism. That's how we know we're at our limit. We reached a mechanism. Yeah? Okay. Now I'll ask the question again. What is the final moment diagram going to look like?
Zero all the way across, because it's only axial forces now, right?
Yeah. How about, let me change my question. The instant before this hinge forms, the instant before, what does our moment diagram look like? Well, how would you find it? Who wants to wager a guess? Knowing what we've been talking about and what we know. How would you find it? Yeah, that's exactly right. It's a summation of the previous moments, so it's the summation of all these moments, and we'll use P1, right? And the L. And then we'll for this one, it'll be the summation of these moments as well, and we'll use P2, right? And then it'll be the summation of these moments as well, which will be P3, right? You're right. You're exactly right. You're dead on. But I can tell you even simply, I know what the moment diagram is going to look like. Moment diagram is going to look like that. And what do you think this value is going to be? M sub P. What do you think this value is going to be? M sub P. What do you think this value is going to be? M sub P. That's what we did, right? That's the definition of structural resiliency, where we keep going until a mechanism forms. We keep going until every piece and part of the member is at their limit. Their limit is M sub P, right? You'd say, hey, but how about this section? Well, you're right. That section's not an M sub P, but we reached a critical event, right? We've lost so much stiffness out of our structure that it now forms a mechanism. Can't go any further. Does that make sense to everybody? This is really, really important. Really important to be able to understand. As a graduate student, you should understand this. You should be able to master this and do this. Okay, what's this for? What do we use this for? Would you ever want to use it for design? Some people are saying no. Cyberspace can't see that. Some people are saying, shaking their head, no. Why not? Well, that's ultimate failure. What are we putting on ultimate failures to make sure they don't happen? Safety factors. If you have a safety factor on this, what's the problem? Very good point. Very, very, very good point. The deformations can cause way more issues, and that's what we're drawing over here. Right, every time one of these events happen, we lose stiffness. What if we put a safety factor on our deformations? What if we do these calculations and we say, you know what, I'm going to say that deformation is the limit, whatever it is, right, for whatever reason it is. We're worried about cracking. We're worried about causing issues, serviceability issues, and other things. We're worried about just stiffness being an issue. I mean, it takes more effort to do those calculations, right? But one could. Wouldn't be that hard to draw this diagram out, right? Hopefully we could all do that because we're going to be doing it on our homework. Okay. Draw this diagram out. One could, and we could limit those deformations. You agree? Right? We could have a limiting P. See, that's the limit. That's the allowable limit. But, I mean, does everyone agree that this is a way to actually squeeze a little bit more juice out of our structure? It's possible, isn't it? Yeah, it's totally possible, and it's done. It's called a plastic design method. Okay, this is used for design. Not often, because it's more rigorous, but a lot of companies, it's all about marketing sometimes, A lot of companies say, we can save you money. They really can't. They like to say that. We can make your members smaller because we can use plastic design analysis. What they really mean is they're going to spend a little bit more time on their calcs. They're going to look at serviceability limit states. They're going to look at what safety factors they need against ultimate failures. And they'll actually be able to use thinner members because of it. And they'll use that as a marketing tool. We know how to use plastic design analysis, and it's allowed by AISC. Okay? So you know how to too. Okay, that's cool. So other than plastic design analysis, other than everyday design, this is a fabulous, fabulous technique to use to look at extreme events like earthquakes, bombs, impacts. Because how do you design for those? Well, we can't design against just the first plastic hinge because a plastic hinge is going to form. Okay? But this technique, this idea, allows us to take our structure to the limit, know what the absolute limit is, and we'd say, you know what, at that point, we don't care about deformations, we just care about not killing somebody. We don't care if they get scared. We just care that they don't die. So this is the only method to look at a 747 impact on your structure. Or a truck bomb impact. Or, some other horrible event that you'd hope never ever happens. This is the only technique that you can use to figure out, they call it shakedown theory. What shakedown theory is that you're taking a structure that has lots and lots of fat in it, and you're shaking it down, and finding the critical elements that need to happen in a row for failure to actually occur. Because when they do, if they all happen simultaneously, we have issues. Okay? Very common technique. It's used. How about in forensic analysis? How about when you look at something that's failed? You want to figure out, was it supposed to have failed? What load was it out? A lot of times people argue that, oh, you put too much load on a contractor. No, I didn't. Yes, you did. No, I didn't. Well, let's find out exactly how much load it should have been able to take. You do this type of analysis and you find out exactly what it should have been able to take. Okay? Very powerful, very common technique for weird problems. You with me? Okay, great. So hey, we just answered that. What has to be true for an event-to-event analysis to be valid? Local and global buckling can't be an issue, right? Or you can't control, at least, right? Have to have plastic hinges. What else? Anything else?
No buckling.
What's that?
Not buckling.
Not buckling? Yeah, that's kind of what we were saying before. How about connections? What do we have to know about connections? You have to be able to take rotation, right? You have to be able to take significant rotation. Okay? And we know how to check that now, don't we? Some of you do. So how do you know when an event-to-event analysis is finished? When you form a mechanism. When you get enough events together, you know enough loss of stiffness to actually form a mechanism, and then it fails. Any questions about that? I'm telling you, it's powerful. It's really powerful. You'll be in a design office someday, and somebody will say, it happened to me. Somebody will say, oh, we have a bridge. We really want to know what size, if an 18-wheeler hit it, would we be okay? Because we're trying to make a decision whether to put a barrier up in front of it or not. What size barrier? Say, can it take an 18-wheeler impact? So you start doing all these, Well, I'll tell you the easiest way to do it is, you take the bridge, you assume the bottom is fixed at some distance underneath the soil, usually about 10 feet, okay? And then you'd say, okay, I've got this connection up here at the top. Well, I'm going to assume it's a pin, because it's easy. It's easy and it's conservative to ignore stiffness, okay? And by looking at the details they use in the Texas Department of Transportation, you would be an idiot to assume it's anything more than a pin, okay? But that's what we do. We assume it's a pin, and then you look at an impact load right here, and you do an event-to-event analysis, and some guy spent 3 days looking at it in a finite element model, and you spend 5 minutes doing an event-to-event analysis, and you're the hero. Because you can do it with a swoop of a pen, right? You work the problem until you get a mechanism, you get the deflected shape, you figure out what the load P has to be, compare that to what a typical 18-wheeler weighs, looking at the traveling at a certain speed, decelerating in a certain time period, very, very quickly you can figure out what that load P would be. Okay? Another rule of thumb, you take the weight and you multiply by 1.5. It's about right. Okay? It's called a dynamic impact factor. You with me? So, being able to take a problem like this that you could literally spend weeks, you could literally spend a whole thesis, oh my gosh, solving, and being able to get within 10% of the same answer in 2 lines is powerful and is what you need to be able to do. You with me? Okay, great. That was fun. Okay, so there's just another example here. Free body diagram, fixed pin, just worked it a little bit different ways. Just, it's good to have more examples. Get the final moment diagram should look like this. You should never miss any one of these problems. I'll say that again. You should never miss any one of these problems. Because you should be able to take all of your previous moments and add them up, and they should equal M sub P and M sub P. You should never miss any of these problems. Okay? And then we talked about how to find this, right? You'd find how much stiffness and deflection that you would get out of this structure, the initial structure. That's going to be the first one. And then the stiffness changes. Why? We've got a plastic hinge that formed, right? Plastic hinge that formed. So now you're going to use this structure with this load. You're going to find the amount of deformation, the additional deformation that happens. That's going to be added on top. Okay? And then once you form a mechanism, you know it's just going to go forever. Okay? So we can have a deformation limit. We can have and we can put a safety factor on that. We can have a absolute limit. We can put a safety factor on that. There's guidance in AIC on how to do that and what to do that. The deformation limit is not so clear. It's really dependent on what your structure is. It's really dependent on how much loosey-goosey you got, how much deformations you can take. Okay? But oftentimes if you have drop ceilings, you can take a lot. Okay? Then it comes down to actually dynamic type analysis. Okay, so you have to have dynamics, like what is the rate of loading? What is that going to change? How is that going to change my natural frequency when I go from this to this? But that's a dynamics problem, not a statics problem. All right? All right. For those taking the natural hazard class, you should have some idea what I'm talking about. Okay. Okay, the ability of a beam to reach its plastic moment is not always possible. So sad, so sad that we have things that underperform in life, okay, but they happen, all right? And recall, as shown previously, that there must be significant strains developed so that the entire cross-section can be plastified. And I do have a physical demonstration, but we're going to wait because we're going to try to do all of our physical demonstrations at once today, okay? But we'll see. Recall, as shown previously, that there must be significant strain developed so that the entire cross-section can be plastified. This is not always the case, as shown below. What I mean by is that if I have a moment on the y-axis and I have deflection on the x-axis, and I've told you before how I love graphs. Oh, do I love graphs? And this is a good one to love. Okay, that when you're loading, this is our idealized case, right? Elastic plastic type behavior, and it doesn't really act that way. Okay, and this is the perfect MCP plastic hinge formation. This is what we want. This is what we're all about. Okay, this is good. This is what we've been talking about previously, but we don't always get that. We don't always get that. We get these cases where we have case 3 where we get up there to be pretty close, but then we have some kind of early failure. We don't get lots and lots of deformations. And a great example of that is lateral torsional buckling, which you should have talked about and know something about. Don't worry, we'll talk more about it coming up. Lateral torsional buckling. And then there are these cases where, and we would say this is inelastic, actually. Inelastic lateral torsional buckling. But where was that again? Remember on our Snell chart, that was the linear part, right? 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 Yeah, the inelastic. That's what this is. 3. Okay. And then we have this thing, this case 2 and case 1. Okay? Now case 1, we would definitely say, and either one of these could happen for case 1 or case 2. Either one. Okay? We could be a victim of something called local flange buckling. We could be, and we could also have lateral torsional buckling. And those are typically, and this would be elastic lateral torsional buckling. How do I know it's elastic? What's that mean? It didn't yield. It didn't yield. It didn't get even to M sub y. Didn't get there. Didn't get there. Okay? And those typically go with case 2, typically. Okay? And then case 1 is typically something that we want to avoid like the plague. And this is called lateral or local web buckling. Local web buckling. You want to avoid local web buckling like the plague. Now, in extreme cases, local flange buckling can also be case 1. In extreme cases, elastic lateral torsional buckling can also be case 1. In extreme cases. But not often. Okay? Not often. This is kind of a qualitative sense, but it's really good to understand where we're going. Okay? And this is a nice bridge to talk about. We've been talking about all this MCP stuff, and now for the rest of the time in beams, we're going to be focusing on 1, 2, and 3. All right? All right. Cool? Yeah. We'll just stay there. Let's talk about each one of them. Beam, case 1 is beam buckles before it actually reaches yield. Typically because of its long length, lateral torsional buckling, some kind of elastic buckling. It could also, like I said, be local web buckling. Two, beam reaches a moment higher than M sub r. What's M sub r? Anyone remember? 0.7 of my is M sub r. 70% of yield. Beam reaches a moment higher than 70% of yield, but not yield, and fails due to either local buckling of the flange or the web. Now, I need to produce some videos that show this, but literally what happens is this never happens, and I'll explain why, but it never happens in rolled sections. Well, almost never happens in rolled sections. This happens in built-up sections, and that's where we're heading. We're climbing the mountain of plate girders, okay? We're getting closer and closer and closer to plate girders, okay? This is a big issue in plate girders, and in plate girders, you choose the size of your flange, and you choose the size of your web, okay? So if you chose it right, actually what will happen here is that this dotted line is where we're loading, and all of a sudden, starts waving at you. Locally, the flange buckles. What happens is that there's compression forces up there. And that flange is only supported here at the center, so it's almost like a cantilever beam. It's almost like a plate. It's got high compression forces coming down, but then it's supported at the sides. Okay? And that load gets high enough and kicks out, wants to move. When it kicks out and wants to move, it tries to twist the entire flange. When the flange tries to twist, the web tries to twist. You with me? The web tries to restrain the flanges. It tries to hold on as long as it possibly can. That's what it does. Flange, but you'll know it's local flange buckling because you'll see the flanges wave at you and you'll see the web wave at you. Okay? Now, local web buckling is really scary. Extremely scary. You're loading, and all of a sudden your web kicks out, your flange rotates, your flange doesn't bend at all, and this is caused by high compressive forces here locally. Okay? That flange just kicks out. Again, think of it as a beam, or think of it as a plate that's restrained at the top and restrained at the bottom, but basically being loaded right here. Okay? It gets loaded, and then it kicks out. Kicks out asymmetrically. You okay with that? Okay. That's what it is. 3. Beam reaches M sub P, but does not allow significant deformations and fails due to local flange or local web buckling, or some forms of inelastic buckling as well. 4. It reaches M sub P, allows significant strains. You have to have case 4 for plastic analysis to be used. You have to have case 4 for plastic analysis to be used. Okay, when sections have local buckling issues, we don't get as much capacity from them. Because what happens when you buckle? You lose stiffness, right? When you lose stiffness, you really can't transfer any more load. And you have to stop. Okay? You have to stop. Well, you don't have to. You can keep going, but you're going to get significant local deformations. But we're going to focus on rolled sections for now and save the nastiness of built-up sections for later. Oh, you're welcome, but don't worry, it's coming. Okay, and you might say to yourself, well, we did rolled sections in undergrad. Why didn't we really talk about this a lot in undergrad? Well, I'll tell you why in a second. Some people do. I choose not to, and I'll tell you why. The slenderness, it's all about, this is really important. This is something that a lot of people forget. Time to wake up out of the haze again. The slenderness, really the width to thickness ratio of either the web or flange determines this behavior. Okay? So, what I'm talking about, and we're going to use these things called gammas. We're not doing anything different than doing something similar to a snail chart. We had an L sub P in the past for a snail chart. We had an L sub R. Remember that? We're doing the same thing. We're just using a different snail chart. This is the second snail chart of apocalypse. Right here. Okay? Actually, the second and third snail chart of apocalypse. Because we're going to have one of these snail charts for local flange buckling. And we're going to use gamma P and gamma R. And gamma for our flanges, the gamma for our flange is B sub F, the width of the flange, divided by 2. Why? Well, because we only care about one of them, like a cantilever beam. Divided by T sub F, thickness of the flange. That slenderness ratio is gamma. Now the steel manual has for us limits of gamma P and gamma R. They're given in table B41. Why don't you box this and triple star it? That table is your friend. It should be tabbed. Okay? That table will give you gamma P and gamma R. Please remember, there's a snail chart for local flange buckling, and there's a snail chart for local web buckling. There's a gamma P and a gamma R for local flange buckling, and there's a gamma P and a gamma R for local flange buckling. And then you have to look at your gamma of your system. This is kind of like L sub B. This is kind of like L sub P and L sub R. And we got to look up L sub P and L sub R in the past in the Z table. And now we're going to look it up in table B41, and it's dependent on the yield strength. Okay? Does that make sense? If you don't get it now, you're going to be lost later. That's cool. That's cool. So actually, there's been certain limits established from empirical data of limiting values where local buckling can be a problem. And they ultimately reduce strength. They reduce strength. If your gamma is lower than gamma sub P, there's no reduction in strength. If your gamma is greater than gamma P, there's somewhat of a reduction in strength. And if your gamma is way greater, there's a big reduction in strength. You with me? You're saying, why didn't we ever talk about this for built-up sections? Some people do. I choose not to. Because for all rolled sections, the web is compact. What does compact mean? That's another way to say gamma is less than gamma sub P. I'll say that again. For all rolled sections, gamma web is less than gamma sub P. That means there's no reduction. Okay? So why even talk about it? There's no reduction. Oh, and there are 6 members. 6 members in the manual that actually have a non-compact flange. 6 members. But this is a total joke, because the reduction for these members is less than 5%. So let me say this again in a different way. There are 6 members, and if you want to, in your manual, it calls them out. These 6 members have a flange that is non-compact. Okay? You're like, ooh, well, we got to watch out for those. They're like the bad people in the class, right? Got to watch out for those. But if you actually do the math on what the reduction is, they don't tell you this in the manual. If you actually do the math on the amount of reduction, all 6 are right there. All 6 lead to a reduction in capacity that's less than 5%. So why do we care? 5% is nothing. I write off 5% all the time. And don't lose any sleep about it at all. It's nothing. So I ignore it. Totally ignore it. Unless I'm doing plastic analysis. Then I avoid the dreaded 6. Right? They're called out for you in your manual, and they're actually, if you look in the Z table, there's like a C next to the ones that don't meet the gamma flange or whatever. Okay, they're slightly non-compact. Now, but why did I even talk about all this stuff? Because we're going to do built-up sections coming up, and when you do built-up sections, these can now control. When you do built-up sections, you're now going to have the 4 Snell charts of apocalypse you have to fight against, right? You have to deal with. Okay, so you'll actually find your M sub P from this. Your M sub P from the other one for the web, the M sub P from the one we know and love that we've used with L sub B's down here. Snell chart looks exactly the same. It's got L sub P and L sub R. We'll use that as well. And we'll find out there was one more. It has to do with shear. Okay? Good. That's cool. Let's talk about beam behavior. In the past, we talked about beams reaching their plastic moment capacity. This is how beams perform if they're short and fully braced and compact. What's that mean? What's compact versus non-compact? What's that mean? It means what zone you're on in this Snell chart. Compact means you're in the first zone. Non-compact means you're in the second zone. Slender means you're in the third zone. You can be compact, non-compact, or slender for your flange or your web. All rolled sections are what? Compact. Except for the 5, right, or 6. Now, we're going to talk about lateral torsional buckling. Some of you have seen this before, some of you haven't. If I have beams that are really, really short and they're braced along their length, then when I load them up, I'll be able to plastify the entire cross-section and I'll be able to get M sub P out. When beams are long and they're not braced, there's no bracing along the length, and I start putting a moment on them, there'll actually be this point that's in high compression, extremely high compression, a point that's in high tension, then a point that's not so much. That's in the middle. Just kind of breaking this up and thinking about this in different zones. So before the section reaches the plastic moment, the top compression section, that's this little column in a sense, tries to buckle. It would rather buckle than stay there and crush. However, the other sections try to restrain this buckling, which causes the cross-section to move laterally and twist. And this, ladies and gentlemen, is called lateral torsional buckling. This said in another way, if we have a cross-section at mid-span, we have compression, we have tension, the top flange actually tries to buckle. This doesn't happen. It can't just jump away. Right? It tries to, though. It's like, I'm not happy. I want to separate. And the other one said, I don't think so. We're a family. We're sticking together. And they all stay together. So the member actually tries to move to the side, but the rest of the cross-section doesn't allow it. Okay? And this is called lateral torsional buckling. And Isabella, please run up to the front. You're my person. Come on. Come on. Hustle, 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 hustle. Picked you because you're fast. You're going to be a moment. Haven't you ever been a moment before? Never.
No.
It's your first time. Okay. We'll zoom in on you, and you'll be famous. Okay. Okay. And as being a moment, you have to apply of bending simultaneously to both sides. Oh my gosh, what happened? Show everyone in cyberspace what happened. Turn, no, rotate it.
What?
Do what I do.
Okay.
Look at that. Top flange is bent. Look at the bottom flange is straight. Do you see it? No, you're doing it wrong. Take the top two,
Uh-huh.
push them together.
Too
Let me
short.
help you.
It's too short.
No. You're just not bendy enough. See how See how the top flange is bent?
Uh-huh.
See how the bottom flange is straight?
Almost, yes.
Should be. Right? Yes?
Yes.
Can you see it? Okay, I'll zoom in even closer. Oh, that's all I can do. Okay, we'll zoom in closer to it. Can't do it. Good
No.
try, though. Good try.
try.
You see it, though, right?
Yes.
You see that it's straight as an arrow,
Mm-hmm.
and as I put the moment on it, top flange moves, and the bottom flange stays straight.
Okay.
You see it?
Mm-hmm.
Everyone else see it? Cyberspace sees it? Okay,